Hello everyone. The title of this video is Using Common Logarithms. Now in this video I'm going to be doing examples taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.3, called Logarithmic Functions, and I'm under the heading Using Common Logarithms. And each example I do is going to be either an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section related to this particular objective. So what is a common logarithm? And we've seen logarithms in some previous videos I've put out from this section, section 6.3. A logarithm usually has a base written with it. Right? There's the words log for the logarithmic function. There's some input, say x, and then usually there's some little number here, a subscript, that's the base of the logarithm. Now, when it's base 10, that's called a common logarithm. So a common logarithm is a base 10 logarithm. Right? And the word common's used because, most of the numbers you ever see are base 10, are decimal numbers. Well, instead of writing log base 10, because 10 is so common, very often you're just going to see log with some input, right, the log of x, with no base. It's like the square root. Remember the square root symbol. For the cube root symbol, you had a little 3 in the index. For the fourth root, you had a little 4. The square root symbol, technically, they could put a little 2 there, but usually it's not written. It's just implied to be 2. So ignoring all that, same thing goes here. In this particular text, when you see a logarithm with no base, you are going to assume they mean base 10. All right? And most calculators as well, graphing calculators, scientific calculators, have a log button, just log. And if it's just straight up log, it is the logarithm base 10 is what those buttons are for. Alright, so the first examples I'm going to do here, I'm asked to evaluate, find the value of these logarithms without the use of a calculator. Alright, so hopefully you recall from previous videos, previous lessons, what a logarithm is. Right, remember, a logarithm is an exponent. A logarithm of some number is equal to the exponent, the power, that I would need to raise the base to get that input. Now remember, the base here is 10. If I'm just seeing log of 1,000 like this, that's base 10. So you got to think, 10 to what power would be 1,000? Well, that's 10 to the third power, so the answer here is 3. Right? And you can change it to exponential form and check. I remember going back and forth between logarithmic form and exponential form. Change it to exponential form and see that it's a true statement. 10 to the third power is 1,000. That's what this will, and that's true. Right? 10 times 10 times 10 would be 1,000. So the value of this logarithm is 3. And once again, I'll say it, and I'll probably say it a lot. Logarithms are exponents. Right? They're the exponent that you raise the base to get the input. Okay. So example 2, very similar problem. All right, again, without the use of a calculator, we can figure out the value of this logarithm. What is the log of 1,000,000? Remember, no base means base 10. So 10 to what power would be 1,000,000? Just count the number of zeros after the 1, right? 10 to the 6th power would be 1,000,000. So the answer here is 6. And again, if you want to check your answer, change this to the equivalent exponential form and see that the exponential form is also a true statement. 10 to the 6th power is equal to 1,000,000. Right, this is true. So the log of 1,000,000 is 6. All right. Hoping this is easy enough. All right, now how about this? We have the log of 100 to the 8th. So 10 to what power? Again, this is base 10. 10 to what power would be equal to 100 to the 8th? Well, let's look at 100 to the 8th for a second and see if we can rewrite this with a base of 10 instead of a base of 100. So that way we'll know what power, what exponent you need to raise 10 to get 100 to the 8th. Well, remember, 100 is 10 squared. So I'm going to replace the 100 in there with 10 to the 2nd power, and that's being raised to the 8th, and hopefully you recall power to a power, some properties of exponents here. This would be equal to 10 to the 16th power, 2 times 8. So the answer here is 16. Right? 10 to the 16th power, and I'll change this to exponential form, right? 10 to the 16th power would be equivalent to 100 to the 8th power. And those are the same, and we see this in this line of reasoning here with the properties of exponents. All right, so that's 16. All right, then finally, on this first page, now I have 2 times, so don't forget to multiply by 2 when we're done with the logarithm. The logarithm base 10 of 0.0001. So remember, this is 1/10,000th, or 1 times 10 to the negative 1, 2, 3, 4, right? This decimal point is 4 places to the left of the point after 1. So this is going to be a negative number, all right? This is actually negative 4, right? That logarithm, since 10 to the negative 4 power is 1/10,000th, right? 0.0001. And then don't forget we have the times 2 still in the front. Right? So this logarithm is negative 4, and then times 2, the value of this expression overall then is negative 8. Okay? Alright, so keeping going with this where we're evaluating without the use of a calculator, and then we'll eventually get into using a calculator. Alright, so number 5 here, what's the log of 10,000? Again, this is just a log base 10. If no base is written, it's a common logarithm, base 10. So 10 to what power is 10,000? Well, that's 10 to the 4th power. All right, again, you can check that out. Change this to exponential form and see if that's true. Is 10 to the 4th power equal to 10,000? And yes, it is. Right, so this is correct. And then my final example where I'm not using a calculator, we have this expression with a logarithm, the log of 1, and then afterwards I'm adding 7. Alright, so what's the log of 1? Now we did see this, something like this, where 1 was the input of a logarithm in an earlier video. Remember, a number to the 0 power is going to be 1, right? 10 to the 0 power would be 1. Right? So this logarithm is 0. And that's the case for any base, log base 10, log base 2, log base 5. If 1 is the input, 0 is the value, 0 is the output. And then don't forget we have this term here, plus 7. And 0 plus 7 is 7, right? So the overall value of this expression is 7. Okay. All right, so now on my next pages, I am just using a calculator, right? Because there are some inputs that are not nice powers of 10, right? In examples 1 through 6, all the numbers inside the logarithm, all the inputs were 10 or 1,000 or 10,000 or 1,000,000 or 1/10,000th or 1, right? They were nice integer powers of 10. So here, evaluate using a calculator, round to the nearest thousandth, right? That's 3 decimal places after the decimal point. So you see here I have the log, right? The common log base 10 of 123. Now we're asked to round this, right? So I'm going to put approximately. Now you can figure out what the whole number part of this is going to be. Right? We know that the log of 100 would be 2. And you hopefully understand that the log of 1,000 would be 3, right? Because 10 to the third is 1,000. So the log of 123, right, that input is between these two. And we'll see later when we talk about graphs of logarithmic functions that logarithmic functions are increasing functions when the base is bigger than 1. So the value of the log of 123 should be between 2 and 3. So I'm going to tell you right now, I know that this is going to be 2 point something. Now what that something is, what the fractional part is, I don't know off the top of my head. Alright, so I'm going to go to that free online graphing calculator at desmos.com and just off on the side here do my calculator. You can just type in log and that's log base 10. And they wanted the log base 10 of 123, and you see how it's 2 point something. Alright, 2.0899, which would round to the nearest thousandth would be 2.090, right? Because the first 3 are 89 thousandths, but then you have 9 in the 10 thousandths place, and that would bump this up to 90 thousandths, 2.090. So this is approximately 2.090 or just 2.09, and that's what they wanted. Alright, and if you change this to exponential form, what this is saying is that 10, right, base 10, raised to the 2.09 power should be approximately 123, right? Because again, we rounded here. And you can see that with a calculator, right? And again, use the calculator you have. I'll just use this Desmos calculator here. If I take 10 and raise it to the 2.09 power, you see how that's pretty close to 123. Right? And if I actually take more decimal places of this, you get closer. So instead of 2.09, say I put in 2.0899. See, now it's 122.99, and then I put 05, put more decimal places on, 11144, and that after so many, after so many decimal places, it'll be so close that it won't be able to round anymore. It's just going to say it's 123. Right. Okay, so it looks like that response, was correct, about 2.090. And that's all I'm doing here for this page. All right, so example 8. What's the log, common log base 10 of 0.04? Now again, I can tell you what this will be between. The log of 0.01, right, which is less than this, this would be negative 2, right? 10 to the negative second would be 1/100th, right, 0.01. And the log of 0.10, or just 0.1, which is bigger than this would be negative 1, right? Because 10 to the negative first would be 1/10. And 0.04 is between these. Right, so the log base 10 of 0.04 is going to be between negative 2 and negative 1. So I know when I go to approximate this, it's going to be negative 1 point something. And then again, I'm rounding this to 3 decimal places. Now you don't have to do all this that I'm doing here. You can just punch it in the calculator like they're asking and round to the nearest thousandth. Right. So back here, just putting in log log base 10 of 0.04, and you see it's negative 1 point something, and it's negative 1.3979, so 398 when I round it to the nearest thousandth. So negative 1.398, and that's all they want. Right. And again, if you want to change to exponential form and check it out, this means that if you were to take 10 and raise it to the negative 1.398 power, you'd get approximately 0.04. Alright, and I'll leave that for you to check this time. Alright, so this last one here on this page, I'm just going to enter as it is. What's the log of the square root of 2? Now the square root of 2 is 1.4 something. So I'm going to tell you right now, this is between 0 and 1. This is going to be 0 point something. Right, but let's just go to the calculator and enter this. So I'm just going to get rid of the 0.04 here and put square root of 2. And this is 0.1505, so that would bump up the thousandths place to 151. 0.151, approximately 151 thousandths. And again, if you wanted to change this to exponential form, test it out. This is saying that 10 to the 0.151 power should be approximately equal to the square root of 2. And I'll leave that to you to check. Okay, and then my last page is just a quick, can you change from one form to the other? And you should be able to. Alright, change from logarithmic form to exponential form to logarithmic form, and that's all I'm asked to do in these last examples. So just write each equation in a different form. So for example number 10, this is in logarithmic form, but notice there's no base on that log. So remember that means base 10. And if I want to change this to the equivalent exponential form, that would be 10 to the t power equals the input of v. And that's it. Very, very simple. You've seen this before. And then example 11, here's a statement in exponential form. And I'm hoping you remember how to change to logarithmic form, right? Remember the exponent gets its own side, right? And that's equal to a logarithm, right? Exponents are logarithms. So a equals the log base 10, right? The base on that exponent is the base of the logarithm. But now when it's base 10, I'm not going to write it. Don't write any base, and it'll be assumed to be base 10, and then 10 to the 8th power equals b, right? So the input of this logarithm is b, and this is what they want, right? This is that's the logarithmic form, the equivalent logarithmic form, right? Remember how these say the same thing, just in a different look. All right, and then finally, 12, same ask, I'm asked to get x alone here, change to exponential form. I have the log base 10, again it's not written, of x equals 3. If I were to change this to the equivalent exponential form, it would be 10 to the third power equals x. And that's all I was asked to do. So you would say that the solution of this equation was x equals 1,000. But I wasn't asked to state solutions or anything, just asked to change forms. And that's it. So you've seen pretty much the same things we've been doing with other logarithms. It's only now you have to just remember that whenever you see log with no base, right, that just means it's base 10, common logarithm. And I'm hoping that watching me work through these 12 examples here helps you in some way when you're working with common logarithms on your own. And thank you very much for watching.